Welcome you to today's video class. I am Sheikh Ejaz Ahmed, working as senior lecturer in mechanical engineering at Government Polytechnic, Nandipet. Today's topic is hardening heat treatment. This topic is from the subject engineering materials from third semester C18 curriculum. Before proceeding to hardening heat treatment, let us understand the meaning of heat treatment. Heat treatment involves use of heating or chilling, normally to extreme temperatures, to achieve the desired result, such as hardening or softening of a material. Heat treatment techniques include annealing, case hardening, precipitation strengthening, tempering, carburizing, normalizing, and quenching. What is the importance of heat treatment? Heat treatment is commonly used to alter the strengthened material's structure through a heating and cooling process. It offers many advantages, which includes change a material's mechanical properties or to modify the mechanical properties, and it aids in other manufacturing steps. It relieves stresses, making the part easier to machine or weld. The stages involved in heat treatment process are three. One is heating, the second is soaking, which is called as holding temperature, holding time, and the third is cooling. Heating is done in a furnace, and during the holding or soaking stage, the metal is kept at the achieved temperature, that is above recrystallization temperature, and the third is cooling. After holding at a particular temperature, the metal must be cooled in a prescribed manner. The different heat treatment processes are annealing, normalizing, hardening, tempering, and case hardening. In today's video class, we are dealing with hardening heat treatment. Hardening consists of heating the steel to proper austenitizing temperature. That is, martensite is the hardest microstructure that can be produced in any carbon steel, but it can be produced only if the transformation of austenite to mixtures of ferrite and carbide is avoided by faster cooling of the steel, which is called quenching. So hardening consists of heating the steel to proper austenitizing temperature, soaking at this temperature to get fine grained and homogeneous austenite. and then cooling the steel at a rate faster than its critical cooling rate. Such cooling is called quenching. Normally, carbon steels are quenched in water, alloy steels are quenched in oil, as critical cooling rate of alloy steel is much lesser. So martensite, having the body-centered tetragonal structure, is hard and brittle. Higher hardness of martensite relative to ferrite pearlite or spheroidized microstructure for common range of carbon steels. Hardness of hardened steel depends on the formation of 100% martensite in it, and the hardness of the martensite depends on the carbon content of the steel. Hardening is done of steels containing more than 0.3% carbon, as the gains in hardness are most sustainable in these steels. Mild steels, which consist less than 3% carbon, tend to be difficult to harden with not much increase of hardness because critical cooling rate is attained with difficulty, and that too in very thin sections by using drastic cooling, which may cause distortion and cracks. Now, what are the objectives of hardening? Hardening is done to all tools, heavy duty carbon steel machine parts, and almost all machine parts made of alloy steels. The main objectives are three. First one is hardening tools is to induce high hardness. The cutting property of the tool is directly proportional to the hardness of the steel. And the second one is many machine parts and all tools are also hardened to achieve high wear resistance. Is the hardness, higher is the wear resistance and abrasion resistance. For example, for spindles, gears, shafts, cams, etc. Third objective is like the hardening the machine components made of structural steels of the pearlite class is to develop high yield strength with good toughness and ductility so that higher working stresses are allowed. But higher yield strength and tensile strength will good toughness and ductility are achieved not in the hardened state but after high temperature tampering of hardened steels. That is, hardening is done of structural steels to prepare the structure for certain transformations which take place during tempering. The tempered structures have high toughness and ductility, the value of which in the hardened state is nearly zero. So tempering is another type of heat treatment process where the component is heated below its recrystallization temperature. After hardening. So now let us have a look on different classes of steels with austenitizing temperature. So the different classes of steels include pearlitic class of steels, highly alloyed steels, carbide class of steels. So we are going to watch the different austenitizing temperatures of these classes of steel. The first one is about the pearlitic class of steels. One of the basic requirements for hardening steel is to first heat to transform the steel to a homogeneous and fine-grained austenite. The austenitizing temperature depends on the composition, carbon, as well as alloying elements in steel, and section thickness. Higher value of the specified range of temperature is used for thicker sections. For hypoeutectoid steels, the temperature will be 20 degrees centigrade above the critical point of temperature. For hypereutectoid steel, it is also above the 20 degrees centigrade above the critical point. That is, for hypoeutectoid steel, it is 20 degrees centigrade more than the critical point EC3 in the iron carbon equilibrium diagram, whereas for hypereutectoid steels and eutectoid steel, it is 20 degrees centigrade above the critical point EC1 in the iron carbon equilibrium diagram. So the range of austenitizing temperature just now discussed for hypoeutectoid steel results in single phase, fine grained and homogeneous austenite, which on quenching transforms to fine grained, that is very fine needle plates, hard martensite, which is desired to be obtained in hardening. Heating hypoeutectoid steels only into the critical range, that is above AC1 but below AV3, is avoided in practice, as the steel then has austenite and ferrite grains. On quenching, the austenite transforms to martensite, but no transformation occurs in ferrite grains, that is, incomplete hardening occurs. If hardening was aimed for high hardness, then the presence of soft ferrite does not permit to achieve high hardness. That is, the hardness shall be low. If hardening was aimed to prepare structure to obtain high tensile and yield strength by tempering, then the presence of ferrite, which has very low tensile strength and yield strength, does not permit to achieve them. In fact, ferrite forms the easy path to fracture. Quenching of hypoeutectoid steels from temperatures much above the required temperatures. When grain coercing of austenite has occurred, results in coarse form of martensite. Such a martensite has high brittleness and a unit or too lower in hardness. The increased brittleness make the steel to have low impact strength even after tempering and more prone to quenching, vaporing, and cracking. Hypereutictoid steels, when heated in the set range, that is just above AC1, have fine grains of austenite and small nodules of proeutectoid cementite. On quenching, austenite transforms to fine martensite, but the undissolved nodules of cementite remains unchanged. As the hardness of cementite, that is approximately 800 BHN, that is Brinell's hardness number, is more than that of martensite, that is 650 to 750 Brinell's hardness number. Such incomplete hardening results in a structure which has higher hardness, wear resistance as compared to only martensitic structure. If the temperature of austenitizing of hypereutectoid steels is increased, but still below a cm temperature, correspondingly increased amount of cementite is dissolved in austenite. Grain growth of austenite may occur as the cementite barriers to the motion of grain boundaries essential for grain growth have largely dissolved. On quenching, coarse grain martensite with a little amount of undissolved cementite and a large amount of retained austenite are obtained. The resultant as quenched hardness of steel is less because lesser amount of hard cementite is present. Secondly, the large amount of retained austenite is obtained as MS and above temperatures are lowered due to increased dissolved carbon in austenite. Austenite is a much softer phase than martensite. Third, the resultant is a coarse grain martensite is more brittle and 1 to 2 units less hard. The quenched hardness is low due to absence of harder cementite, much more retained austenite, and martensite is much coarser. So the second austenitizing temperature for highly alloyed steels we are going to discuss now. The first comes the austenitic class of steels. In this alloy steels, austenite is a stable phase from room temperature to high temperatures. Austenite does not undergo phase transformation, neither on heating nor on cooling. So no grain refinement is possible by phase change. The main aim of heating is to obtain single-phase homogeneous austenite at room temperature. For that, these steels on slow cooling, as in casting or even on heating to 500 to 800 degrees centigrade, participate carbides, generally on the grain boundaries of austenite. Such carbide participation causes a decrease in ductility and impact strength, depletes the regions close to grain boundaries of, for example, chromium in stainless steels, decreasing the corrosion resistance of the regions causing intergranular corrosion. Presence of double phase instead of single phase austenite further accelerates corrosion by forming micro galvanic cells. Next, about the carbide class of steels. These steels are mostly alloy tool steels such as high-speed steel, having iron 0.75%, carbon 18%, rough iron 4%, chromium and 1% volatile metal. Such a steel bases its high rate hardness on secondary hardness, in which the magnitude of increased hardness depends on the fine and uniform dispersion of as much of alloy carbides as possible to block the motion of dislocations. Now let us talk about the heating time for hardening. The total heating time should be just enough to attain uniform temperature through the section of the part to enable not only the completion of phase transformation but also to obtain homogeneous austenite. It should not be longer to cause grain growth, oxidization, and decarburization. The total heating time includes the soaking time too. During initial heating upstage, the surface of the steel is at a higher temperature than the center. The closer the temperature of the steel becomes to the present temperature of furnace, the smaller is this temperature difference. That is, in actual practice, it can be assumed that when the surface has reached the temperature of the furnace, the steel is heated right through based on calculated values. Heating time to hardening temperature of 850 degrees centigrade in an alloy fired muffle furnace can be obtained. You can see in the figure. The diagram is good for plain carbon and low alloy steel. The time to heat to the temperature depends on the shape and size of the parts, the composition and structure of the steel, arrangement of parts in the furnace, and the type of furnace. The soaking time depends mainly on the composition of the steel and its original structure. Soaking time depends on the desired degree of carbide dissolution. Since the amount of carbon is different in different types of steels, the soaking time thus depends on the grade of the steel. So for round bars, the total heat time for the furnaces like electrically heated furnace, it is 40 to 50 seconds per mm. And for internally fired furnaces, it is 35 to 40 seconds per mm. And for salt bath, it is 12 to 15 seconds per mm. And for lead bath, it is 6 to 8 seconds per mm. A practical guide of time is when the component has attained throughout the required temperature. The color of the part is indistinguishable from that of the furnace wall. Otherwise, the part is darker. The soaking time begins when the surface has attained the present temperature. In salt bath too, the color of the part is matched with the color of the transparent liquid salt. Plain carbon and low alloy structural steels contain easily soluble carbides and thus need a soaking time of 5 to 15 minutes. So let us have a look on the table of soaking time. So as discussed, plain carbon and alloy, low alloying structure steels have 5 to 15. whereas medium carbon alloy steels have soaking time of 15 to 25 minutes, and low alloy tool steels have zero point 0.5 or 30 seconds per mm in that way. Now let us have a look on components for hardening. The surfaces of the tools and components should be clean and smooth and should be free of the foreign materials such as scale, sand, etc. by cleaning with wire brushes or in sandblasting machine, as their presence interferes with the quenching process and decreases hardness. The cleaning process has a special significance for components requiring development of uniform and high surface hardness. Oil, grease, wax, etc. can be removed by rinsing in caustic soda added hot water. Holes in components and tools are increased tendency to cracking, particularly when water quenched, as hardening occurs first there. Such holes may be packed with wet asbestos, clay, or steel inserts to avoid hardening inside them. Threaded holes are blocked by screw plugs in them. Many times, special fixtures are made to hold the heated parts to be immersed in cooling tank to avoid distortion. Small-sized parts are often put in pans or on iron sheets to be heated and then simply poured into the cooling tank, which already has immersed netted basket or easy withdrawal from the cooling tanks. The components having small cross-sectional area with long slender length, such as small tool bits, screw tips, etc., require quenching to be done in exactly vertical position and need to be fixed in fixtures such as illustrated in the diagrams. Special tools with sharp hits or center punches are used for withdrawing large-sized parts from the furnace and putting them in quenching tank. Normal tongues, if used, may not only produce soft spots, but in some cases even cracks at the contact areas due to large difference in cooling rate. Now let us talk about the relieving the internal stresses or internal stresses occurs during quenching. Internal stresses are always produced due to non-uniform plastic deformation. In quenching of steel, the non-uniform plastic deformation may be caused by thermal stresses or structural stresses, but usually by the combination of both factors. Internal stresses development is a very serious problem in hardening heat treatment, since they often result in distortion or cracking or even premature failure of part in service. If a steel is cooled slowly, the temperature distribution across the section of the part can be regarded to be uniform. Thermal and structural volume change then occur uniformly and simultaneously throughout the section, hence no internal stress is set up. Cooling in quenching takes place non-uniformly, that is, causes temperature gradient across the section. Surface layers contract more than central part and at different times, which leads to non-uniform volumetric changes. The contraction of the surface layers is restricted by the central part. It puts the central part under compressive stresses and surface layers in tension. If the stress level becomes more than yield stress of steel, non-uniform plastic deformation occurs. The plastic deformation is neither simultaneous nor the same throughout the layers of the cross section. As the central part is still contracting, the stresses may become smaller. At times, the surface layers may come under compressive stresses after reaching zero level, while the central part be under tensile stresses. The stresses that develop in a quenched part as a result of unequal cooling, which causes temperature gradient and result non-uniform volume changes, are called thermal stresses. Structural stresses are the stresses which develop due to non-uniform volumetric expansion due to phase change and at different times when the steel is rapidly cooled. Here the three cases are considered through hardened steel, shallow hardened steel, in which transformation occurs simultaneously at the surface and the center. Third is the shallow hardened steel, in which transformation to pure light occurs earlier in the center than martensite at the surface. So let us have a look on this. So the first one is through hardened steel. The figure here illustrates the cooling of surface and center of a cylinder superimposed on CCT curve of steel 0.77% carbon. As the cooling rate even in the center exceeds the critical cooling rate, the part is completely hardened up to the center. Here, the volumetric changes in the piece and the distribution of stresses from the surface to the center at different stages in cooling. In stage 1, surface and center are cooled rapidly to result in temperature gradient. Only thermal stresses are produced as the surface is prevented from contracting as much as it should be the center, putting surface in tension and center tender compression. That is illustrated here. In stage 2, under this stress, the center may get plastically deformed as it is still ductile austenite. After stage 2, brittle and hard martensite in surface thermally contracts while center is still contracting. This leads to slight increase in stress levels. At the beginning of stage 4, stress center has attained MS temperature and begins to expand, forming martensite while surface is still slowly contracting. The center, as it expands, puts the surface in tension and stress levels are considerably increased. In stage 5, the center is contracting thermally and the surface is almost at the room temperature, which leads to decrease in stress levels. And many times it may even reverse. These graphs are oversimplified as the actual distribution of internal stresses at different moments of cooling are more complicated. The stress difference, particularly in stage 4, increases as the dimensions of the bath and the rate of cooling are increased. Now let us talk about the shallow hardening steels. In it, transformation takes place simultaneously to martensite in surface and perlite in the center in stage 2. In stage 1, thermal contraction of surface and the center leads to surface in tension and the center in compression. In stage 2, entire piece is expanding, but an expansion is more in of the surface layers due to its transformation to martensite. That is, surface tends to expand more than the center. It puts the center in tension and surface comes under compression. In stage 3, as the center is thermally contracting, the surface is almost at room temperature, prevents the contraction as much as it should. Higher tensile stresses develop in the center, which is perlite of relatively low tensile strength. The greatest danger now is to produce a tensile crack in the internal central part, but cannot come to surface because of prevalent compressive stresses in the surface. Next is about the shallow hardening steels. In this, the transformation has completed in the center to 100% perlite before the surface starts to transformation to martensite. The center has expanded in stage 2. In stage 3, martensite starts forming in the surface. That is, expansion occurs of the surface layers. The final result is that compressive stresses increase considerably at the surface, while the center is under tensile stresses. Of the three cases, the maximum stresses are developed when the steel is too hardened for the same size of part. Several factors affect the magnitude of internal stresses developed. Expansion occurs when austenite transformation to martensite, but it occurs over a range of temperature, and higher is the temperature of transformation, lesser is the expansion due to the corresponding change in lattice parameters of austenite and martensite. That is, higher is the martensite transformation temperature of the steel, the specific volume changes are smaller and thus there is reduced danger of quench cracking. Increasing of carbon and alloying elements lower the temperature, make the steel more prone to quenching cracking. The presence of high carbon not only aggravates by lowering temperature but also increases the brittleness of martensite, increasing the tendency to quench cracking. The time of holding the quenched steel part between room temperature and 100 degrees centigrade, if increased, then quench crack tendency increases. The probable reason is additional strain produced due to formation of martensite by isothermal transformation of methane aldehyde. The development of internal stresses during hardening cannot be fully avoided, but can be reduced by using different methods of cooling, such as tempering, etc. Industrial practice, wherever practicable, perform surface hardening or not through hardening tools and the machine parts if it can give good life in application. This is because the usually compressive nature of internal stresses obtained in these methods make the surface layers to bear greater amount of tensile stresses. That is, the strength of the surface is increased. This advantage, which increases, thus the life of the part is used, for example, in leaf springs by short pinning the surfaces to induce compressive stresses before putting them in actual service. This is what about hardening heat treatment process, especially of steel. That is, martensite structure is converted into austenite to increase hardness property of steel. So now let us once again have the brief go through about today's video class. So we have started with the introduction to heat treatment, which is heating or chilling to extreme temperatures to achieve desired results, such as hardening or softening of material. The other heat treatment process other than hardening are annealing and normalizing. The importance of heat treatment is to modify the mechanical properties of materials and to reveal the internal stresses developed due to cool working process. The stages involved in heat treatment for any kind of heat treatment process are heating to above recrystallization temperature in general and holding at that particular above crystallization temperature for some time, which is called soaking, and then cooling. The cooling may be slow, very slow, or fast, and depending upon the cooling, the heat treatment process is named. As said, there are many heat treatment processes like annealing, normalizing, tempering, case hardening. In this video class, we were discussing about hardening heat treatment process. Now, when we talk about hardening process, we are talking about heating the steel to proper austenitizing temperature, soaking at this temperature to get fine grained and homogeneous austenite, and then cooling the steel at a rate faster than its critical cooling rate. Such cooling is called quenching. Normally, carbon steels are quenched in water and alloy steels are quenched in oil. Martensite, having body-centered tetragonal structure, is harder and brittle. Higher hardness of martensite related to ferrite or spheroidal microstructure of common range of carbon steels. Hardness of hardened steel depends on the formation of 100% martensite in it, and the hardness of the martensite depends on the carbon content of the steel. The objectives of hardening steel is to induce high hardness, and to achieve high wear resistance, and also to develop high yield strength, and good toughness and ductility. Now, the austenitizing temperature for different classes of steels were discussed. The first one is austenitizing temperature for pearlite class of steels. There, we have discussed about hypereutectoid steel and eutectic steel and hypereutectoid steel, where in hardening it is heated above the critical points AC3 and AC1 to 20 degrees centigrade above AC3 or AC1. Heating hypereutectoid steels only in the critical range, that is above AC1 and below AV3, avoided in practice, as a steel then has austenite and ferrite grains. On quenching, the austenite transforms to martensite, but no transformation occurs in ferrite grains. That is, incomplete hardening occurs. So that is the reason this range should be kept in mind. So the result of quenched hardness of steel is lesser amount of hard cementite is present, large amount of retained austenite is obtained, and coarse grain martensite is more brittle. So now the austenitizing temperature for highly alloyed steels, that is austenitic class of steels. Here, a stable phase from room temperature to high temperature, that is the austenite, does not undergo phase transformation neither on heating nor on cooling. No grain refinement is possible by phase change. The main aim of heating is to obtain single-phase homogeneous austenite at room temperature, and the heat treatment called quench annealing is limited only to austenitic class of steels. Let me talk about carbide class of steels. These steels are mostly alloys, tools, steels such as high-speed steel, and its high red hardness on secondary hardness, in which the magnitude of increased hardness depends on the fine and uniform dispersion of much of alloy carbides as possible to block the motion of dislocations. Now we are talking about the heating time for hardening, that is soaking time. So it depends upon the type of furnace. The soaking time for electrically heated furnace is 40 to 50 seconds per mm. For a round bar material, for internal fired furnace it is 35 to 40. Salt bar type of furnace it is 12 to 15, and for lead type it is lead bath it is 6 to 8 seconds per mm. The soaking time, the total heating time we were discussing in the previous table. So this table we were discussing about the soaking time. So the soaking time for plain carbon, medium carbon, low alloy tool steels, high alloy chromium steels, hot work tool steels, and high speed steels are listed here. And we were also discussing about the components of hardening. During hardening, what were different components? If it was a very small size, we use the tray. Otherwise, we use these kind of fixtures during hardening. So as discussed, the hardening is used to remove the internal stresses. But because of the quenching, some internal stresses are also developed in the components during hardening process. So internal stresses developed in these phases are discussed here. So the three cases are considered there. That is the through hardened steel, next to shallow hardened steel, next to shallow hardened steel, in which transformation to pearlite occurs earlier in the center. So these were the graphs discussed, and this is about today's video class. And have a nice day. Thank you.